Haha! Here we are! Excellent. Looks like we've got some people already on here. Hello, everybody. This is Thomas, just checking if everything is working. Excellent. Just quickly share it to my Facebook. Excellent. Just quickly share it to my Facebook. And there we go. All right, so we've got 16 of you so far. This is amazing. Thank you. Oh, 18. Nice. Welcome, everybody. We're going to get started properly in the next few minutes. Let me turn that down so I don't double up too much. I'm going to be keeping track of how many we get in here, and if you have any questions about today and the stuff that we're going to be doing, don't forget, for everybody that is kind of new or is watching one of these streams for the first time, this is a great opportunity to visit MakerKids.com. There are links in the description of this video as well that will take you where you need to be. All right, and we're getting a drum roll down to 2 p.m. Ready, 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 ready. And man, you know, time goes slower. Maybe this is just the thing that we've all been dealing with. Time feels slower. There we go. We're at 2 p.m. So, welcome everybody who is watching right now. My name is Thomas. I am one of the teachers at MakerKids. This is my third live stream on our MakerKids official YouTube. Today, we'll be covering one of our most popular topics, robotics. Robotics is the future development of so many different technologies in our world that are here to help us. And I'm going to talk a bit about some of the basics today, and then I'm actually going to get into some live making as well, where I'm going to try to make something called a theremin. It's a musical instrument that is controlled by light waves, or like the strength of light in a certain area. So as I go through that, I'll be kind of like talking my way through it, explaining what I'm doing as I'm going along. And if you have your own Arduino robotics kit, then absolutely that's a great time for you to be trying to tinker along with me. Now, talking about robotics. So I always ask kids, like, when they come in for the first class, it's like, what do they think a robot is? And they're like, you know, a robot is a cyborg-like being or android that walks and talks like this, moves really joltily, and has arms and legs. That is a very particular type of robot. That robot is called an android because it's meant to look as human as possible, and they are some of the coolest robots out there. And they're really cool because they kind of remind us of people. And that's always the easiest kind of robot to relate to and be like, wow, this is what took a lot of work to make, and this took a lot of interesting technology behind it to be able to duplicate what humans can just kind of do by watching each other and learning and practicing a little bit as we grow up. Like when we learn to walk at when we learn to walk during like our first 12 months or something, it's a really big achievement. But teaching a robot to do that, much trickier. So androids are not the only type of robot out there. In fact, they're very, very rare and very hard to build. The most often types of robots that you see in your day-to-day life are most things in your house. Computers, cell phones, your microwave. All of those are robots because they have these things in common. Step 1. They are powered by electricity. Yes, there are some robots that exist before then that were powered by like steam or spring power or like water wheels and stuff like that. There's some very ancient, really cool designs you can look up. But all robots these days are made with electrical power. Step number 2, a robot is made to help us do things. A robot is there to, is built by a human and so it's man or woman made, and it is made to help us accomplish tasks or to do something that we don't want to do, or that's too dangerous for humans to do. And that's really another reason why they're so great. And lastly, most importantly, coding. A robot needs coding. A robot needs programming because it needs to have a list of things that it's supposed to do. And it knows to do them step by step. Probably starting from the top to the bottom, go step by step. So that's what a robot is, and we're going to get into talking about the types of robots that we make at MakerKids and the types of robots that other kids have made. So at the beginning of MakerKids, you can join in to a mini makers class, the grades 1 to 2, where we're working with a program called Microbit, which I might actually still show a little bit of later today as well. But today I'm mostly going to be focusing on Arduino, which is another type of robot brain that we can code and wire things to and make some really, really cool inventions. Wow, there's 27 of you right now. Excellent. So let's get into, let's break this down point by point. The first one we talked about was electricity, right? Here is my super, super fast explanation. You can, if you forget any of this, you can get all of this in one of our free trial classes. But right here, I've got a circuit. The first thing I've got on my screen here, as you can see, is a little coin cell battery. Hello, coin battery. And we've got wires connecting both sides of it to a little light bulb called an LED. Now, this circuit is one of the most basic examples because in order to understand it, we just need to know some very simple things. A battery, no matter what type of battery you're using, has two sides. It has a plus and then a minus side. The minus side is where the black wire is, also known as negative. And the red side, or the plus, is also known as positive. Now, these are the two sides of the battery, and if you really wanted to get finicky about it, then we could talk about how the first people discovering electricity and discovering how to you work with it and use it and store it might have gotten the whole positive and negative thing wrong. But we still use the positive and negative as our two sides because it's very easy to imagine where electricity is flowing and how it works. In fact, the way that we like to teach electrical flow and everything is the same way that electricians learn to use it. They learn that electricity in a battery or in any circuit starts on the positive side, and then it wants to get to the negative side. So as it's trying to go there, there's a wall that's stopping it in the middle of the battery from getting there, and so as it's trying to run into it, it's just like, I gotta get over to the negative side. Ow! Oh, there's something in the way. There is a wall. And that wall is pretty hard to get through. So all we have to do is connect up some wires and give it a path around the wall, which is what I've done here. So this wire is going to give the electricity a way to go whoop all the way up the red wire into the light and down the black wire into the other side. And as it does that, the light will turn on. A very simple bit of understanding of electricity allows us to make a simple circuit like this. But with robotics, we take that, 18 steps further over time. And the great thing about any class like this, you start off with some smaller steps, you work up to the harder ones. So let's move to one of those projects. Boop, there we go. Now, this is where I get to talk about what I'm actually using here to build the robots. Look at all of this stuff. Isn't it neat? Wouldn't you think my collection's complete? This, my friends, is a website called Tinkercad. Tinkercad is often used to make 3D printing designs, but they also have a very, very awesome portion of their website that allows you to build circuits. And they built it off of an old website called circuits.io, but the great thing about this is it's got everything that we use in our MakerKids classes already as a digital component. A component where you can not only wire stuff up to it, you can code it online, and you can even simulate what it would do in real life if you had everything plugged in properly. It's a really, really good simulation. So let's start off with one of the very first things. This is the Arduino. Now, some people might say it looks like, I don't know, it looks like a computer chip. And yes, it absolutely is. It is a chip, also known as a microcontroller, but I always like to refer to it as a robot brain. Now, just like your brain, or any animal's brain, or any living thing that has a brain, unlike some jellyfish, I think, any living thing that has a brain is controlling every other part of their body with tiny little bits of electrical impulses. They send them down through your nerves and make your hands tense up. That's you shocking your tendons and your nerves just a little bit with electricity from your brain, and then relaxing. Shocking, relaxing. Tensing up with a little shock and relaxing. If anyone's ever gotten a static shock or been accidentally a little bit electrocuted, you'll know your muscles tense up. That's the same sort of effect. Now, a robot brain, though, isn't using nerves or, tendons or anything like that. They're using wires. And on a lovely app like this, on a lovely website like Tinkercad, drawing wires and connecting wires to things is super duper easy. I just have to tell it I want it to go here, and then here, and then here, and then here, and if I don't like it, I can hit backspace to get rid of the wire and the most recent curve of it that I drew. So, with the Arduino, just like our brain can control many different things at once, many different fingers, many different toes, all of the different muscles in your body, and even regulate all your organs and everything, the Arduino has many different things that can be plugged into it. As you can see here, we've got all of these different pins. These are the ways that I'm going to be sending electricity, which normally I would get by plugging my Arduino into my computer, and these are the way that I'll send some of that electricity out to different components, different pieces of the robot. If you wanted it to be the pieces like the servos of a robotic arm that went then you would probably need to control one servo for the elbow, another servo for the rotation of the hand, and a whole bunch of micro servos for all the different parts of the actual finger joints and everything. And then each of those could have their own pin that they're plugged into. As you can see, there's 13 on here, and a whole bunch of other ones that will be very useful later on. But here's what we're going to get into: a basic thing, and then the fun build that I had in mind for today. So, let me just show you the very basic. If I take this little light, this is my little LED that I had from before, and I plug it into these two pins, GND and 13. GND is our negative pin on the Arduino. It's the ground, where the lightning, which is electricity, strikes from the clouds down into the ground. That means the ground is the finish line, which means it's negative. And I've also made the connection through the light into 13, which is just going to be our easy positive pin, because any of these ones from 0 up to 13 could be positive if we turn them on. And now, it's very simple to actually get this light to turn on. All we got to do is go to Code, which is a handy-dandy thing up here, and I've already got something built for this. This is saying, and I'll just zoom in for people who really want a good view of it, this is saying set built-in LED to high, and then wait 1 second, and then set built-in LED to low, and then wait 1 second. This is something we do in our first trial class. We want to get the light to blink. And the reason we need... here's how it'll go right here. Take a look. The light is blinking. Perfect. Now right here, this is the first thing we start with because it is the first time that you are actually giving robotic programming to a robot. It is doing this automatically. Like the moment I plug it in, the robot just keeps doing it, and that by definition means it's doing something robotic. If I just told the light to turn on, I wouldn't really need a whole robotic brain to do that. I could just plug it into a battery like I did before. So here we go. This is our first bit of robotic code. Now, we're going to take this even steps further, though. This is a fun little light. I could make it blink faster. I could make it blink slower by changing how long it's waiting before it does the next thing. Important bit of code there. But let's take it further. As I said, If you hear my cat in the background, I apologize. His name is Stormageddon, and he is just all over the place sometimes. But anyways, let's get into this. I'm going to actually rotate my Arduino so that you can read the pins a bit better. And then I'm going to get some other blocks and other code and get started by making the project I talked about. I'm going to make a light sensor-based theremin. So if you don't know what a theremin is, then I highly suggest looking them up. They are really, really cool instruments that were used to make all like the ghostly sounds of like 80s horror movies where they go like, and this will be some music. I'm hoping my audio isn't too loud, so maybe I'll just quickly check my audio levels. They make those types of sounds, and that is pretty loud. I was definitely peaking a little bit there. But we're going to try to make that with the robot, so that if I was changing the amount of light that was that the robot was being exposed to, or the amount of light in the room that it's in, or like maybe briefly putting a shadow over it, then it would actually change the pitch of the tune that it's playing, making it go higher or lower. So let's get started. I'm going to start off with connecting up something called a breadboard. Fun story about the name breadboard. This doesn't look like bread, and it is not made of bread. No, that is not what it is for. However, there is some history behind that. There is just the very simple story that when people were first learning to make circuits and they were trying to be like, how do I organize my wiring? I don't know why they talked like that, but they did. They were like, how do I organize my wiring? I've got all of these things and I don't know where they're supposed to go. I know that I want this wire to go connect to this thing, also routed through this thing. What they did was they took these old bread cutting boards, which had holes in them to catch crumbs. So literally from bakeries, they would buy these or borrow them. They'd slice the bottom off of them, and underneath they would attach long strips of metals called rails, like rails on a track, right? And right here, as you can see, if I mouse over the positive row, which we can see has that familiar symbol, we can see that all of these light up from top to bottom. That means there's an entire row from positive to positive, where if I plugged something into here, it would be connected all the way down in this entire column, top to bottom. Same goes for negative. But when I get over to these ones, the numbered ones, you might think, well, the letters here look like they'd be helpful. Maybe it's like letters as well. We keep going with columns. No! We switch over to horizontal, to rows. So each number is a row unto itself, and then it's separated by this little bridge in the middle, and there's a secondary row over here. Now this is going to be very important as we go through our wiring, because we'll need to make some interesting connections as we go. So here's my first one. I'm going to do the positive and the negative. Now, little warning of this, I'm going to be using 5 volts of power. This is a positive pin on the Arduino that uses the most power you can get from it. That uses the most power that you can safely get from it. So 5 volts of electricity is a good amount to work with. And so what I'm going to do with it is I'm going to connect it up to positive right here, and I'm going to turn the wire red, because red is a pretty standard color for positive. And for the negative, as I said before, I'm going to use GND. Dynamite, GND. All right, here we go. There's the black, and I like to use black for GND because that's also standard. That's what most people use. All right, so I've got my positive and my negative connected up. Sometimes hear people saying like your positive and your negative power. That's kind of a misnomer, because there's no such thing as like positive or negative power. There's just a circuit, and it flows from positive into negative. But now that we've got that hooked up, we're going to connect the first component. It's called a light sensor, or if you really want the more complicated term, a photovoltaic resistor. That's my nerd thing. But yeah, we're going to use a photovoltaic resistor or a photoresistor because it resists the electricity that flows through it. Now this thing is really, really cool. And we have like a whole bin of these at MakerKids on site as well, both locations. And when you use these, they are made of a certain type of material where when they are exposed to light, the particles, all the little molecules in there get super excited. They're like, sunlight! Yay! And they just start dancing around, and they make it much easier for electricity to flow through it. And if there's less light in the area, they're like, oh, it's dark and I'm scared and I'm tired. And so they don't let as much electricity through. They are resisting more of it. So here's what I'm going to do. I am going to plug this in to, let's go with rows 8 and 9. Not that the numbers of the rows really matter, because again, these numbers are just here to help us organize. And then I'm going to make a very simple connection. On one side of this, I'm going to have power flowing into it from, boop, right from there. Right from 5 volts. It's going to be getting directly 5 volts of electricity trying to flow through it. And then as it comes out the other side, whoop, I'm going to attach something else. I'm going to get a normal resistor. So remember, this one is a photoresistor, and this one's a normal resistor. Now this will be important, mainly because like we want to be able to control, and I think 1k ohm is good. Yeah, ohms are a measurement of resistance, how much electricity is stopped by going through it. And just while yeah, this should be good. And then at the other end of this, I'm going to be measuring how much electricity actually managed to get through this circuit. So again, it's flowing along this wire, all the way up here, into this red wire, all the way along here, through the photoresistor, along to here, and then some of it is going to go just straight along here, and go into analog pin 0. To make it simple for you, this is just, analog pin 0 is just going to be the pin where we have a measurement of the amount of electricity that's managed to get through the photoresistor. And then over here, we're going to have our negative. So the negative is actually being controlled by going through the resistor. That's important. Okay, that looks good to start. And so basically, like, the main sort of thing with this is, since the photoresistor is actually kind of using 3 different terminals, the electricity coming out of the photoresistor has a fork in the road and can decide whether it wants to go through over to A0 by going just down this link and all the way to here, or into GND by going through the resistor and then along the way to here. Now, as some might realize, if you give electricity an option, it's going to take the path of least resistance, right? In order to get somewhere, it's going to take the path of least resistance to get where it's going. So it's going to actually split some of that as it goes, and some of it's going to flow through the resistor into GND, but most of it's probably going to go into A0, and then we will measure what comes out. It's like sending in a bunch of people into a yeah, let's go with that. It's like sending a bunch of people into a game of tag in like a closed gym, and then like a game of manhunt or something, and their goal is to get outside. If you're analog pin 0, you're the guy standing by the door where they have to escape out of, counting the number of them that escape, and be like, oh, okay, all right, about 8 of you escaped. Really quick, good job. And that's what analog pin 0 is doing. It's measuring. Great. So that's more of an explanation than you really need, but I want to be thorough with you guys. So let's just test this. Since we've already built the first part of this and we want to make sure our light sensor is working. So now we get to code. This is the part where you maybe start to realize that the coding part of this looks very familiar to some of you. We know that a lot of TDSB schools and places all over Toronto have been using Scratch as a really awesome tool to teach your kids code. We teach that as well, as part of our coding program, and there is a stream from 2 weeks ago where I was doing some video game development on my boss fight for a cool space game I'm making, or at least I think it's cool. But for this, we're going to be using blocks that are also based on the Scratch system. They work together, and they snap together, in order to make your code really easy to parse or to understand. So, let's get started with the first thing. I'm going to be making something called a variable. This variable is just a box that I'm going to call, let's go with, don't try to restrain a sneeze, people. Let me just make sure my audio didn't go out there. There we go, we're good. So I'm gonna make the variable, and I'm going to call it light. There we go. Since what I'm measuring is the amount of light, sometimes measured in lumens or candle watts for some things. But anyways, we're going to be measuring it, and this will give us our photoresistor reading. And I'm going to say that at the beginning of my code, I want to set the light to the reading that I'm getting from analog pin 0. Very easy. So what I've done here is all I've done is really created a little box of information, which actually fits right into this lovely little oval-shaped block, this little egg-shaped block for Easter. And I've told it that, hey, I want you to always be checking the amount of electricity going into analog pin 0 and save that into a little box called light. And that number will be able to constantly change. And then afterwards, I'm going to have that thing get printed out. So I want to be able to see where my information is coming out, so I'm going to use this. The serial monitor. Yes. Cereal monitor. Not the cereal monitor, breakfast cereal. As you can see, it's spelled a little bit differently. And this is just a simple way for me to keep track of it and say, print a serial monitor. I could just print hello world. And then if I simulated, you would see hello world, hello world, hello world, hello world, hello world. Or other robot voices I can do, hello world. Right? But we don't want it to say hello world. We want it to say something useful. Information for us. So I'm going to use this. You'll notice when I dragged a new block in while I was simulating, it stopped the simulation. So I've always got to restart. Let's simulate again. It's going to do all of this in a loop. Also a reminder for those of you who've used some code like this before or done a bit of robotics before, Tinkercad already has a built-in loop. So you don't need to worry about loops, but you might need to worry about like if you've got stuff in setup later on. If you don't understand that, don't worry. And right here, perfect. Here's my simulation. It looks to be working pretty well. And I can change the light level. So the further I go towards the sun here, the more of a sunburn I get. Or in this case, the higher my numbers are going. So if I was to like have this in real life, then I would be like shining a flashlight over it to test it or bringing it out into the sun. And see right here, this is already a very, very good way of being able to measure the light level of things. A useful invention not only for photographers who really need to know the light level in a room, but also one of my favorite ones. We've had a kid who I heard developed something where he had the light sensor set up on the inside edge of his window. And then had a servo motor connected to his blinds. Those type that can just be like rotated on like a little gear to like make the blinds close like this. Like go shunk, Venetian blinds they're called. Shunk, like that, closed, or shunk, open. And so he had, when the light level reached a certain amount above, like when it was morning and the sun was coming up, he'd have the blinds automatically go shunk, like that and close. So many, many different things you can make with this, but today I'm turning it into a musical instrument because that's my jam. So, here we go. Let's move to the next step. This is already working. I can already keep track of the light level of things. I'm tracking the amount of electricity that goes through it. Let's keep it moving. So, for the next step, I'm going to be actually making the speaker connected up to this. So, and I also love to explain speakers. This is one of my favorite things to explain, actually, is the idea of how you make sound with robots. And in fact, how robots can learn to make different sounds. So, and in order to do that, I always like to explain the basics of sound. So, when I make sound, when I'm talking to you right now, I'm doing a lot of different things with my body. I'm using my voice box, which is a muscle that vibrates. And then those vibrations travel in the air that's in my lungs and everything. They get pushed past things, and then the sounds that I'm creating rise up into my throat, where I can shape the sound a bit more, and then up to my lips, my teeth, and my tongue, where I can make all these different consonant sounds and turn those into words. But the main thing that's coming out of my mouth is vibrations. Vibrations that travel through the air and into this microphone and to your ears back home. But those vibrations in the air, if we could see them, they would look like ripples in a pond. Like very fast ones usually, but they would travel outwards and grow wider and wider and wider, like spreading out from the epicenter of the sound where it was created. And they could bounce off of things and do a whole bunch of stuff. But when we're making music, there's a really interesting thing we do. When I'm singing, or when I'm playing an instrument, or when I'm even like plucking a rubber band. In fact, I might grab a rubber band because that's a really good one as an example. I'll find one in a moment. But when I have when I'm singing something, that voice box in my chest is vibrating at a certain speed. And yes, I may not have promised in the stream that I would sing that much, but I'm going to a little bit. I'm going to a little bit today. So let me just back the mic off for a sec, and I'll lower that a little. Okay, so if I'm singing low notes like this, oh, all I'm doing is vibrating this muscle back and forth at a pretty slow rate, maybe like a few hundred times a second. Like it's moving back and forth a few hundred times a second. Muscles can do that. And then if I do a higher note, right, I am vibrating it faster. My muscle is moving maybe 600 times a second. In fact, it's pretty easy for us to demonstrate this because we don't have a voice box here, but what we do have is another piece of our we have another piece of circuitry that we can add to this called a piezo buzzer, or a type of speaker, really. And your speakers that are in the headphones that you're wearing, or in your computer, or in your car stereo, are very similar. They're just a little electronic thing that is meant to vibrate back and forth. They are meant to go up and down at a very specific speed, and it's a speed that we can control with a robot that thinks very fast. So, let me wire this one up here to show you what I'm talking about. So again, I'm just going to connect it up to two different rows here, and I'm going to just keep this one simple today. I think I'm going to go with connecting this one to pin 9, and then this one, since 9 will be my positive pin, I need my negative pin, which, as we remember, can just be the negative right here. It's fine because it shares the negative with the other things in our circuit. So there we go, I've got a buzzer. Now the coolest part about it is that the way the buzzer works is with something called electromagnetism. When we turn on the power for pin 9, it's going to turn on an electromagnet, a magnet that is only on when electricity flows through it. And then while it's on, there's another magnet underneath it. So electromagnet here, normal magnet here. And when the electromagnet turns on, the normal magnet goes right up to the top. Turn it off, falls back down. Turn it on, and we do that hundreds of times per second. Super fast. Like back and forth so fast that you really couldn't even see it. And at a certain point, that becomes a vibration of a tone, of a pitch, of a tune, of a melody. Like it'll make a sound like, if I just give you a basic bit of code here, and I go to output, I'm going to use play speaker. Here we go. In fact, maybe let's just do that. Yeah. Play speaker on pin 9 as I used with tone. Let's not do 60. Let's do my favorite, 440. 440 is the most popular. So here we go. Let's try that out. Ah! It is loud. good thing to note with that. This can be pretty loud. In fact, a little useful thing, if you are testing this, I highly suggest right-clicking on your sound settings, going to Volume Mixer, and then lowering the sound for whichever streaming or whichever site you are using, whichever browser is what I meant to say. So let's try that again. Let's hear how that sounds. Well, that's a very specifically. It's a good pitch. It's a good tone. It's meant to be the A above middle C for anyone who plays piano. And I can even test it. Pretty sure my little piano here is out of tune, or slightly out of tune, but it will be close. So let's just double check how out of tune it is. So, middle C right here. Oh, middle C right here. A, the one I'm talking about, is right here. And what did that sound like? Well, it's close. There we go. It's, as I said, close enough. Definitely need to get this thing tuned. But yeah, so I've made my connection here, and now it's actually pretty simple to just make a slight adjustment to this. I want it to play a different tune as we go along, and let me just see the audio levels when I do that. There we go. I turned down the desktop audio. We're going to make it make much more pleasing sounds by actually being able to control it a little bit more, alright? So, the one that I'm going to try with this is I'm going to make something called a map level. Since as we saw before, the numbers I was getting from here went down to as low as 6 sometimes, and went higher other times, to 517. Having a little magnet vibrate about 6 times a second isn't fast enough to create a tone that we can hear. We need it to be at least a few hundred times, or maybe just above 100, so each second. So here's what I'm going to do. I'm going to very simply get my variable and try it like this. Play speaker on pin 9 with tone light. This is the frequency. The light, the number we're getting here in our serial monitor, the number we've saved in our variable, is going to be changing the actual pitch, or it's going to become the actual pitch. So whatever it says here is the speed that this buzzer is trying to vibrate. Okay? Let's see how this goes. Oof, as you can see, not working so well. Not working so well. We need to do a little bit more fixing. In fact, right now, it's getting too much, and it's sometimes getting too little. So we need to do something called limiting it. We need to map the number that we're getting and make it a bit smaller. Now, mapping is a great thing in math, where you turn one range of numbers into the ratio they get, the percentage of a certain range of numbers into a different range of numbers. It's like someone asking you, it's like, hey, easiest way would be someone says usually on our teams, on our sports team, about half of the kids really attend our practices. It's like, oh, how big is your team? 60 kids. Okay, so 30 kids attend your practices. And then if they say it's oh, we got 100 kids this season. Great. How many of them are still attending practice? Still about half of them. So, since there's 100 kids now, then the half is 50, right? So it's the same ratio, it's the same percentage of kids, but it's the different number of it. That's a basic idea of mapping something. So I'm going to map this here by telling it, play speaker on pin 9 with tone pin, and I'm going to say map the number from light that we're getting from the light variable, and map it from a range of let's go 50 to 70. I think that would work decently well. And let's see how that goes. And then, in fact, actually, I think it might be better to do this as a separate variable. Yeah, that's what I'm going to do. So I'm going to make another variable called sound. Or maybe I'll call it, just to teach some of you a new word, frequency. Because what I'm controlling is the frequency, the speed of those vibrations. So I'm setting the frequency to map the light number, this number down here, and change it to a range between 50 and 70. Very good. And I'll play the speaker, unpin that with tone frequency. For 1 second, yeah, I like that. Let's see how this sounds now. Better. Beautiful music. Don't you agree? Well, if not, then, yeah, you're probably right. It's not beautiful yet. We need to add a few more things. First of all, one thing that is going to be a little bit of a problem right now, when I turn this invention on, it's not, it doesn't have an off switch, right? I would have to unplug the Arduino from its power source. I would just, and when I press stop simulation, that's the same sort of thing, but we can make this better. We could add a very simple on-off switch, which is not too hard to do, actually. On-off switches are like drawbridges. They're just a very simple way for you to tell a circuit to either be able to flow by having a set of wire connected, like that, or not be able to flow by disconnecting the wire. And usually they'll have some sort of mechanism attached to them that can like push that bit of wire down so it's making a connection and letting electricity flow along, or it's lifting up that connection and stopping that flow. And we're going to use a very, very simple slide switch. A pretty common one to use. So I'm going to rotate this here, and I'll connect it up down here. This should be good. And then very simply, for the middle pin of any of these like 3-pin switches you'll ever find, they're usually negative. The middle pin is pretty much always, if it says it's the common one right here, that's the negative. So here we go. And then for this one, we're going to go, let's use pin 2 for this. Okay? Perfect. There we go. So we've just got a very simple circuit. And the way that this will work is we are going to be telling the robot to try to send power out of pin 2 all the way along here. It's going to flow up along this wire into the switch and down into negative. And it'll be able to complete that flow if the switch is on. If it's off, as I described before, whoop, then it won't be able to. Good. I like it. All right. So programming it, not too hard at all. The idea of this is that we want to use a read input block from this group, the input group, just like we did for the analog pin as a input source. And we want to check if electricity is flowing at pin 2. Like if the electricity is actually flowing out of there. Because remember, the thing about electricity is if it's got nowhere to flow, it will not go. If it's got nowhere to go, it will not flow. Also works. And if we don't have the switch turned on, then the electricity won't actually bother to flow out of pin 2 at all, because remember, electricity is lazy. It's lazy. So, let's do this very simply. Yeah, because that's a good way to do things. I'm going to get an if statement. All right, but the first thing I must do is I must set the pin 2 to high so that it is ready. So that it is ready to send electricity out of it when we turn it on. And then, remember, even though if we set it to high, it won't actually flow unless it has a way to get to GND, which currently it could. So now I'm going to get, from control, one of our most useful blocks, actually, an if statement. An if statement is also very simple to use. It is very simply put a statement that says, if this thing is true, or if this thing has been done, then I will do this stuff, the stuff I put in here. Now we also have something called an else added onto this. So this is an if-else statement. Else is not Elsa. The snow glows white on the mountain tonight. Not that. Some kids always ask me that. It's not her. The else is actually just otherwise or instead. I could do an if-then statement that says, if my cat is making noise, then I will lock him up in the bathroom temporarily. It's okay. He's fine. He has water. Else, he can come on my lap and I will pet him. Or other if statements. I will say, if it is rainy, then I will bring an umbrella. Else, I will put on sunscreen. Yeah. Or if I am hungry, then my stomach will grumble. Else, I'll be full. So we use these statements all the time in our day-to-day life, and often people get scared of them when they're first doing coding, and it's like, this is something that you use all the time. We just need to learn to put it in simpler words. So here we go. We're setting pin 2 to high, and we're asking it that if I'm reading something from digital pin 2, like if I'm getting power from digital pin 2, so I'm going to go to input and get read digital pin 2, and if it is equal to 0. So if I read digital pin 2 and it equals 0, that means no power is flowing out of it, then I want this to start playing. This might not make sense because to you possibly, because you might be thinking, wait, that doesn't make sense. We want this to turn on if electricity is able to flow out of this. And yeah, 0 basically means that pin 2 can't reach the ground. Right? It means that I think the best explanation of it is it has a lot to do with the way that we've described positive and negative, right? So to make it not confusing at all, this will work, and if you test it the other way, if you're ever doing something like this and you test it with if read digital pin equals 1, which means 1 means electricity is flowing, you'd find it wouldn't work as well because us setting pin 2 to high actually reverses the logic of the circuit. But just for now, just trust me on this, since the full explanation is trickier than I want to get into today. So after, when I need to decide what I want it to do when the switch is not on, which is, very simply, I want it to turn off the speaker. And I need to tell it to control the same pin. The speaker's pin 9. So there we go. If switch is on, do all this. Else, turn the speaker off. Okay? So let's see how this is going. Perfect! So I think that's working really well. Yeah, it's able to pick up the sound when I do this. I can change the level. And turn it off whenever I want. Yeah, now, the distortion that you get from this is just kind of an inevitable thing with this. But again, this is mainly meant as a tool for testing builds and stuff like that. So you're not going to get the absolute prettiest sounds out of a simulated program like this. But it is still working quite well. Now I could go even further with this. I could make the amount of notes that I can access a little bit bigger. 50 to 70 is actually still pretty good. But I think that playing around with something like maybe 50 to 240 could be interesting. Let's see this. Maybe not. Let's go back to what we were doing before. Pretty sure that Tinkercad handles this differently because that's definitely not the frequency I chose. Although since it is mapping the ratio of it, yeah, that might be why. All right, yeah. So, yeah, I think I'm going to keep this the way it is for now, and then I might move to showing you guys some other stuff. I could set pin data to map light to range. Ooh, that's possible. I'm always just looking at a few options that I have. So yeah, how about we add something even cooler, like maybe a button that causes the speaker to play a different sound. So that's not too hard to do. We could just, oh yeah. Let's add this on. Because I think people will like this one. It can get a little bit crazy, and I know people love a little bit crazy. So I'm going to go in and get a push button, which is a very simple type of button here. Rotate it around this much, and I'm going to attach it, let's say like right above the button. I think that'll work pretty well. In fact, I might need to make a bit more space for myself, because see, I can't plug it in right here. The buzzer's in the way. I could plug it in, right here. Yeah, none of those rows are being used. We're good. Cool. So just like before, with this switch, this button is also going to need, it's also a bridge where when I push the button down, it's a different type of bridge though. This time, the bridge is always disconnected until I push down. When I push down, it connects. When I let go, there's a spring that pops it back up and disconnects it again. So push buttons are a little bit different. And I'm going to have it work like this. This part will be connected to pin 3. Let's give it its own color. That hasn't been used. And then this part, as per usual, will be GND. There we go. And the coding for it is going to be fairly similar as well, actually. I'm going to need to use pin 3, and I'm going to have to try to send power out of pin 3. So let's set pin 3 to high so that the button can know that electricity is trying to flow there. And then inside of all this, I am only going to want this thing to play, this button to work, if I am actually pressing the button, and only if my switch is on as well, because I want the switch to be kind of like the overall mute, where no one can make any sound. It's a good way to like transport it and stuff like that, and make sure it doesn't accidentally turn on the moment you plug it in. So here's what I'll do. I'm going to take another if statement, another if else, and I'm going to put it right about, let's go with, set light to read analog pin 0, yeah. Sure, this will be changing the set sound. I like that. Yeah, now the reason I'm doing this is because what I'm doing, so I'm going to use an if statement, but I'm going to put the if statement inside my other if statement. This is called nesting if statements. And the reason we do this is because I'm setting the frequency normally by the light sensor. This button is not going to be using the light sensor. I'm just going to have it play like a random tune. So it's kind of like a different part of my soundboard that I'm designing. So if both of these things are controlling the same buzzer, if one of them is telling it to vibrate at a frequency determined by the serial monitor down here, and the other one is telling it to turn on like by a frequency of like something else, they're both controlling the same thing. So I need to have only one happening at a time. So very easily, I'm just going to say, I'm going to duplicate this, put it here. Instead, I'm reading digital pin 3. And then if read digital pin 3 equals 0, then I'm going to want it to set the frequency to this. Okay. And then afterwards, I want so this is what's going to happen if the button is being pressed. It's going to map the frequency from, let's go 70 to 90. And then for this one, we'll do 50 to 70 as well. We'll keep it normal for 50 to 70 here. So pressing the button will get us a different frequency. All right. Cool. And then for this, we're telling it to play on speaker pin 9 with tone frequency for 1 second. Good. Also, we might use another little thing here. We might use pin 6. What do we want to? Challenge. Oh, okay. That could be interesting. Yeah, no, we don't need to do that one. So this will work fine. Cool. All right. Let's test this out. I think this will work fine the way it is. So now that we've got it connected, let's do a test. and press. Turn it off for a moment, because again, that's still pretty loud. All right. And let me just turn down my desktop audio a bit more. Let's try changing the frequency a bit. Ooh, okay. So, when I press the button, it's definitely changing the range. So pressing the button, as you can see here, maps to a different range of frequencies, to a different range of notes that the Arduino, that the buzzer can vibrate at. That's really cool. Okay, so that button works pretty solidly. Well, I think, you know what? I'm pretty happy with this build. It's able to do what I want it to do. If I had it hooked up to my actual Arduino in person and like maybe a different quality of buzzer on here, it wouldn't sound as like warbly and stuff like that. And I could actually turn this into a good bit of a musical instrument. Now, since we have about 7 minutes left in the stream, this is where at the point where I want to show you some other things. So I have a few other projects that are already completed, and thank you for watching my live tinkering as I'm like figuring some stuff out and doing a bit of what I like to call being Tinker Thomas, the nickname that some of the kids gave me. I think I remember who gave it to me, but I won't say his name. But yeah, it was a good nickname, and I will hold to it. So I wanted to show you, as I said, some other inventions that other people have been working on. One example, and this is like what Tinkercad's menu looks like, that I'm really a big fan of, was this one. Also a type of keyboard. So let me take a look at this. And let's see if the simulation in here will work. So this one has multiple different buttons hooked up to it. And here we go. Start simulation. And it seems like the code has some errors. All right. All right, so we might need to like rework with that one a little bit more. But this one would be an example of a very simple build where you could like play a digital keyboard. Another great example of programs that other kids have been making. Let's go with... Oh, yeah. I already had this one open. Here we go. So this is the code and the wiring for a really fun build that has something called an RGB LED. An LED that can change colors, and each of the different colors of it are controlled by these potentiometers, which are variable resistors that can change which of the different three-color LEDs are in here. So as I said, this one's called an RGB LED for red, green, blue. And we combine, so that means there's one red LED, one green, and one blue LED. And since they have like 4 different wires coming out of them, as you can see, this one is meant to go to negative. The other 3 are each controlled by a different digital pin, so that we can control how bright each of those other little LEDs are. As some of you have experimented with color mixing in school, if I do a bunch of red and a bunch of blue, I get purple, right? And you'll find that there will be some slight differences with light, because light is it's definitely different than mixing paint, to say the least. So, but as you experiment with it, you'll notice that we can change the colors of this light. So let me show you this one in action. I will start the simulation. Here we go. So the light is kind of like teal-ish color right now. Let's add a bit more of this. And then now it's kind of yellow. A bit more of this. Ooh, now we're a bit more into the blue. Okay. Let's try a bit more this way. And now let's put this one all the way full up as well. And this one all the way full. And now we've gotten to white. So see, with all of them all the way, this is full. Like at this dot, that's full. And like right here, this is the lowest. The great thing I actually just noticed about these, if you really zoom in on them, you can notice that if you're curious which part of the resistance of a potentiometer, or a pot, as some people call it, you can see that the brightest ones, that's where we're getting the least resistance. And then the further I go down, I'm getting more resistance. Excellent. So, let's play around with that. Sorry for hitting my mic there. And so look at that, we can get a whole bunch of different colors. I love this build. This one is really satisfying to put together, and once you're done it, it works so well. And this button right here, pressing it causes the colors to just go random, which is also really fun. These are the types of things that, you might be like, okay, so you've got a light that can change colors. What can you do with that? Let me tell you what you can do with that. Not only can a different color of light be a signal for different things, like you could play a game of red light, green light with a robot. You could turn it into, like, you would maybe want, like, a different light color changes for some sort of security system on your bedroom door. That way you know red means someone tried to get in. And that green meant everything was good. You could use it to make, what was the other example I was thinking of? There's many different ideas, but yeah, you could even use it just to make like a fun little game, like a game of Simon Says, where you have to like do the same color. Really, the possibilities are endless. Or you could add it onto a cosplay. That's the one I was thinking of. I've seen some people who made really awesome things. Like someone made their own Buzz Lightyear costume, where they had his like gauntlets and like the laser on there, so that when they pressed on a button there, they had like powerful LEDs like that, changing colors and like flashing and doing all this stuff, and making the sound effects that his like arm blaster does. So a lot of great ideas to come from that. And let's show you one other, because we've got a whole bunch of different really fun builds in here. And then I might even tell you guys a short little story about MakerKid, who went very far with his builds. Okay, I think the only remaining one of this is this one. So this one right here, this one's really, really cool, because what it is capable of doing is it's capable of broadcasting text onto an LCD screen. So I've gotten it to say robotics and then inches, because what it's capable of doing is actually measuring distance from objects with this ultrasonic sensor up top. And it operates on the same principle as like a bat's echolocation. So a bat can bounce sound by going, ah! But like really, really high pitch, like super up there. And then those sound, like we talked about before, those like really, really high pitched ultrasonic frequencies of sound will come out of their mouth, bounce off of objects in their environment, and go back to their really big ears. And their brains are really good at turning that into visual data. So it can tell, oh, this is the shape of this super, super dark cave that I can normally see well in, but since there's absolutely no light, I know where stuff is, I know where my friends are. I can even find that tiny little fly who's flying around and eat him. And with this, we use the same principle. One of the little things here is a speaker. The other is a microphone. One will shoot out the ultrasonic sounds that are so high that you can't even hear them, bounce off an object nearby, and then come back. And then the robot brain is capable of figuring out how long that sound took to travel to one place and come back. And with that information, it can figure out how far away it is. In fact, it's a trick that one of my math teachers in high school was able to pull off by like shouting in a canyon and having a really precise timer. He figured out the width of a canyon that we were in. It was crazy. But it's otherwise usually pretty hard to do. So that's why we use robots. And then this one will be a great readout, which will tell you on the LCD screen how far away an object is, or how far away the wall is. A really useful thing to have if you're building one of our Red Rover kits. Now this is actually a really cool thing, and this will be the last thing I show you. On MakerKids.com, there is a robotics kit that you can get through us, through one of our local providers, that has a drivable robot kit, which is what we want to work kids up to in the curriculum, especially at MakerKids in person, to be making drivable robots where maybe on the front of them you could have a sensor like this, which could, when the robot gets up to a wall, go, boop, we're too close to a wall. Back up, turn again, and drive somewhere else. And it'll act just like a Roomba, like those little robotic vacuums, right? That's a really fun project that we get kids doing about like a few months into their classes. Okay, so that's not connecting, but that's okay. So that is actually, oh wow, it's already 3:02, guys. That is all for today. I made one build with this, showed you off some other builds that you can make on Tinkercad. We hope to have some more of you joining us for robotics and starting to make some of your own creations as well. This type of stuff is actually easier than it looks, and I hope I was able to show you that. I gave a lot of extra explanation, but the great thing about MakerKids is that there's no quizzes or tests that you need to be stressed out about when you're coming into this type of stuff, so you don't need to remember everything I said today. Whatever you did absorb is going to be useful at some point later on. When you're making stuff like this, understanding is important, but actually making it work and maybe just even understanding that the electricity needs to go from positive over into negative, that'll be a great starting point for you. And as we go into the coding, we always help with this. We show diagrams, we show pictures for you, and the instructors are very, very good at helping your kids through the different steps in order to make the robots work. So, thank you all for coming today. I hope we've all learned something. I hope my singing wasn't too loud or too distracting, and I hope my robot wasn't too loud or distracting. But I hope you have a good day either way, and we'll see you next week when we come back to a new stream, which will be announced by the end of today. Thank you, though. Have a great day. Keep making.